is frozen again. God dang it. All right, here we go. All right. So yesterday we went through a couple of reactions. We talked about epoxide opening and epoxidation. And we also went through this reaction wheel. So let's look real quick, finish off that top reaction. All right, so we know we did the epoxidation. What we didn't do was the second part, which is epoxide opening. Right, so we just have a simple nucleophile sodium methoxide. When we talked about epoxide opening, right, what are the two sets of conditions that we have to think about? Anybody?
You said what are the opening? Can you say that question again?
I was asking about the epoxide opening. Right, so we have an epoxide, we want to open it. There are two sets of conditions, either what? Neutral or acidic. And this is neutral. So where's the epoxide going to open if it's done under neutral conditions? Which side?
The right side?
The right side?
Oh.
Yeah, come on. Don't be shy.
I would say the right side because that carbon
It's less
has
substance.
less thing. Right? Yeah, it has less stuff that is bonded to.
That's the observation. If you open it in epoxide, if you do it under acidic conditions, it's going to open on the most substituted side. If you do it under neutral conditions, it's going to open on the least substituted side. So for this reaction, the methoxy anion, sorry. This is going to open right here, boom. And then it's going to pop that open, pop the ring open. And then eventually you'll treat the ring opening product with an acid to quench it. Because your epoxide opening is normally going to end and result in the formation of an alcohol. I keep striking out with these pens. Okay, so the OH should be here. And then the OCH3. Okay, so anytime you open an epoxide, it's going to be either neutral conditions or acidic conditions. And if it's done under neutral conditions, it's going to open on the least substituted side. If it's done under acidic conditions, it's going to open on the most substituted side.
So where did the H come from to give that oxygen on a H?
Yeah, so normally this would be O minus once you pop the ring open, but after you will have to do a quench. All right, so you just add in some H plus.
Okay.
So under neutral conditions, you'll add the acid after the opening. Under acidic conditions, you add it prior to the opening, and that's going to change the regiochemistry.
Wait, so under acidic, you
start out with acid. Let me go back to here, to the when we talked about it yesterday. So right here, if you look at the conditions up top, where it has H plus first, and then the nucleophile, and you see where the nucleophile open on the most substituted side. And then on the bottom reaction, you have the nucleophile first and then H plus. So that's how you get your proton on your alcohol. Are you following or no? Is it not making sense?
I'm understanding, yeah.
All right. Let's go to another question. Let's do this question right here. When methylamine is and Z5-phenylpent-4-ene-2-on are reacted together, a shift base is generated. Shift base is this product right here. I can call it an imine, or you can call it a shift base. Either one, right? All we're doing here is putting in arrows. So how do I get from 1 to 2?
Is that nitrite?
Hmm?
Is it a nitrite reaction?
Nitrogen?
It attack.
So again, let me give you a way to think about this. So a carbonyl is always going to be an electrophile, right? So if you got an atom in the presence of that carbonyl that has lone pairs, like a nitrogen or oxygen or some other nucleophile, it's going to attack the carbonyl, right? So in order to get to 2, you can see that there's a new bond here, right? Between nitrogen and carbon. You can see that right here. Right, so that means that the nitrogen had to attack the carbonyl carbon, followed by the pi bond breaking. Right, anytime you attack the carbonyl carbon, you're gonna break the pi. What's the name of that intermediate? It's common to all carbonyl additions.
Tetrahedral.
It's a tetrahedral intermediate. You're gonna get that tetrahedral intermediate every time you react a carbonyl with a nucleophile. Right, now, what happens after that is, that it varies. It can eliminate, where you reform the pi bond, or you can protonate it, or you can do, in this case, what happened going from 2 to 3? Look at 3. What happened? So this is 2 right here. This is 3 down here. What does it look like happen?
Proton transfer.
Proton transfer. Very good. Inter or intramolecular?
Intra.
Intra. Good. So come on now, pen. Do right today. It's Wednesday. Bible study day. Right? So you did a proton, intramolecular proton transfer to get you from 2 to 3. right? You know the crazy thing about this stylus? So I paid like $40 for a stylus from Amazon. It was electric, got plugging in. I don't know what I did with it. I sat it down somewhere. I looked at on my desk and I found like 10 of these little bootleg ones that I bought a long time ago that are, kind of like with the rubber tip. And I didn't spend a nickel. I was gonna buy another one of the other ones, but I might as well just keep this one. Anyway, that's a tangential point. So we did an intramolecular proton transfer. Look at going from 3 to 4. What did I do there?
Another one.
Another one. Sound like Cali. So boom, here, and then need to zoom in on that so I can get it for that arrow properly. Right? Another intramolecular proton transfer. Now what do you think I have? What have I set myself up for? Right?
Dehydration.
Dehydration. Because now I have a good leaving group and I can use the electrons on nitrogen to force it out. Boom, just like that, to make that carbon nitrogen pi bond and lose water as a leaving group. Right? So it'll be the shift base plus H2O. Now let me ask you this question. What type of reaction class does dehydration fall under?
I said nitrites earlier, but
So let me help you with that. So you got 4 types of reactions, right? Substitution, elimination, addition, rearrangement. What class of reaction would the dehydration fall under?
did you say
Elimination.
substitution?
It's actually okay. So
Elimination.
it's an elimination. Good. Okay, let me show you why it can't be substitution. Let's go back to the beginning. Do you see here that we're starting with a sp2 carbon? Right? If you start with a sp2 carbon as your electrophile, you can't substitute. You can only do addition or elimination. Right? Oh, that's sloppy. Only addition or elimination. Right? So that's just a rule of thumb. Anytime you have a sp2 hybridized carbon, you can only do addition or elimination. You can't do substitution. Another giveaway that it's a addition followed by an elimination is that you end up with only you end up with 2 products, but for the addition part, you took 2 things and added them together to get 1 thing. You see how you went from 1 to 2? So you went from 1 where you took 2 pieces and you form that intermediate in 2. That's a sign of addition too. But you start with 2 things and you get 1 product. Right? And elimination is the exact opposite. You start with 1 thing and you end up with 2 products. Water being one of them, and then the ME. All right. Any questions about that? Y'all been kind of dragging a little bit lately. I know it's a lot going on, though, so I ain't tripping. It's a lot going on everywhere. All right. Let's keep going on this worksheet. I think this gonna take us home. What we got? When we finish 17.
Yep.
All right. So we got did we start this? So is it time for an exam Friday? Or did we just took an exam Friday, right?
Yeah.
Okay.
That's
So everybody,
literally last week.
everybody woke up on that one. Exam? Somebody just stretched and yawned and then unmuted. What? Test? So yeah, it'll be next Friday. We're actually gonna get a chance to cover something that I haven't covered in I don't know how many years. Whew. But it's gonna be fun though. All right, let's go to here. This is a multiple choice question. And then we're gonna look at the reaction underneath it. What do you think? 2 moles of alcohol, 1 mole of ketone. What type of reaction is that?
It's one acetyl and then one hemiacetyl. Acetyl.
Yes, yeah. 1 is hemiacetal, you're right, and 2 is acetal. So which one of those is the acetal?
One.
Good. Who was that?
One of them.
Good. Very good. This is the product right here. It's the acetal. Can't stress enough. Make you some flashcards and do it and keep looking at them. Keep getting reps in. The reactions ain't gonna memorize themselves. Mechanism wise, the flashcards may not be the best way. Doing mechanisms is muscle memory. So writing out the arrows over and over again, different problems. But learning the reagents and the outcome, that's straight memorization. And there's no other way around that except to make some flashcards. Or you can even download. How many of y'all downloaded the flashcards I recommended in the syllabus?
I made my own.
You made your own. Okay, cool.
Mm-hmm.
But they also have there's 2 apps. I think one of them is Organic Chemistry Reactions, and one of them is Organic Chemistry Flashcards. And both of them, one of them is free, one of them is $5. Good. One of them is free. One of them is $5, but they both serve the same. The free one works just fine. All right. All right. Okay, let's go here. Let's see if we can figure this out. It says complete the reaction sequence shown by supplying the proper reagents in the blank spaces. So let's work. Looks like my screen is frozen. Hold up a second. It's been freezing up a lot lately. All right, let's go to, we're doing this question right here, right? It says complete the reaction sequence shown by supplying the proper reagents in the blank spaces. So if you look at the first reaction, what type of reaction is that? You got phthalimate followed by sodium hydroxide and water. What do you think? Let me help you, because I'm just gonna circle that because the name of the reaction is right there. It's a Gabriel synthesis, right? So what is Gabriel synthesis used for? It's used to synthesize. Ooh, that looks bad.
Yes.
Go ahead.
To make primary amines.
Mm-hmm. What? Synthesis of amines from what starting material?
Halide.
Speak up. You're right.
A halide.
Alkyl halides. Good. Right. So it's the synthesis of amines from alkyl halides. Also said you could do primary or secondary amines also. All right. So here's the amine that we made through Gabriel synthesis. What's the alkyl halide? Right. If you remember, that amine came from here. Let me just capture real quick. Sorry about that. Come on. That amine came from there. And after the first step, and then in the second step, that's when you pop that phthalate open to release the amine. So so how did I get to here? Right? So the question I'm asking is, what alkyl halide did I start with? Right? I can deduce that from the amine, can't I? Did I start with that?
Does it have to be BR or do you just
No.
choose?
It can be iodine, it can be chlorine, or bromine is probably gonna be your best halogen.
Mhm.
All right, are we following that, or is everybody
Mm-hmm.
just like jumped off the boat and just swimming on your own? So for Gabriel synthesis, those are your reagents. You need the alkyl halide, you need phthalate and a base, right, to prepare phthalate to be a nucleophile and react with that alkyl halide, right? That's what gives you this intermediate right here. This reacting with the alkyl halide. Come on, screen. Why this thing keeps freezing? Crappiest computer in America. One of them, anyway. All right. All right, let's go. Let's look at the next reaction. What am I doing? What am I doing if I take that primary amine that I just made from phthalate and 1, 2, 3, 1 bromo, 2 methyl propane? What am I doing with that amine, that primary amine plus that ketone? What reaction is that?
Shift spaces.
Yes. Shift-based synthesis. Primary amine plus aldehyde or ketone. It's gonna give me amine. So what does the product look like?
Okay, so
None of that changes except what?
The NH is where the O is going to be?
The nitrogen is going to replace oxygen. Very good. That's exactly right.
oh yeah.
All right. For a bonus question, just let me see if everybody will wake up for that. For a bonus question, if you show me the mechanism, and let me just say this about mag sulfate right here, don't get caught up on that. Mag sulfate is a desiccant, so it absorbs water. So every time, let me show you, so you know you're gonna get H2O2, right?
Mm-hmm.
So every time you make H2O and mag sulfate absorbs it or gobbles it up, what does that do to the left side of the reaction? It forces it to make more water. It's Le Chatelier's principle, right? So don't get caught up on the mag sulfate. This is the part that I care about right here. That plus that. The mag sulfate is just in there to facilitate the reaction. If you write out a mechanism for this and turn it in today by 5, you take that for as a bonus assignment. Don't use mag sulfate. Mag sulfate is not involved in the actual mechanism, so don't touch that. Right. I'm going to make a link on Blackboard after class. All right, we good on that? Always good on bonus points, right? All right. Let's do the next question. Draw the major products derived from the epoxide opening with either.
I'm so sorry. Could you go up one time? Just go up. Sorry. Just trying to
That's
recognize.
okay. There's no need to apologize.
Okay. We're good.
Mm-hmm. All right. So it says draw the major products derived from epoxide opening with either methoxide or LAH shown below. All right. So I can't remember which video it was in, but I know LAH is in there. What is LAH used for? That's this lithium aluminum hydride. What is that used for? Anybody? So we use that as a hydride source. A very good one, actually. And very highly reactive. Okay, it actually looks like this, where you have aluminum with 4 hydrogens around it. It's negative, and then lithium is just a counter ion. Highly reactive. One time I was working with this, my first time working with it. This is why it's good to always read the safety and MSDS information on anything you work with. So I'm working with this stuff. I run a reaction. I thought I quenched it. And I'm working on a milligram scale. I thought I quenched it. So when I go to the sink to wash my dishes, the LAH was kind of crusty, kind of like a white residue. So I put the water into the flask to wash it, and it went everywhere. I mean, it was like a geyser. That's how reactive it is with water. So highly reactive source of hydride. A hydride is this, right? It's a hydrogen nucleophile, H minus, right? So, question is, what conditions am I working under if I'm working with LAH opening at epoxide? So it's basically H minus going attacking the epoxide.
Neutral.
Neutral conditions. Very good. All right, I'm under neutral conditions. And I'm just gonna put this down here so you can, I don't want to
So
screw
can
it.
you explain how would I be able to identify neutral versus acidic?
Okay, again, if it's neutral, sorry. If we're working under neutral conditions, right?
Mhm.
Look at the order of reagents. You following? See what number one is LAH itself.
Oh, okay. Yes, I remember.
You hear me?
So you just have to pay attention to that to be able
Order.
to identify.
Yes, you look at the
Okay.
order of the reagents. If I had the number one sulfuric acid, H2SO4, and then follow that up with LAH, then we're talking about now, oh, okay, now I'm working under acidic conditions.
Mhm.
Right? It's always about the order of the reagents. Look at the other reaction on the other side, right? It's just sodium methoxide, right?
Mhm.
There's no acid present. So that's also going to be under neutral conditions. What does that mean for the opening?
It's gonna open on the least
The
substituted.
left.
It's going to open at the least substituted side. That's exactly right. So both of these are under neutral conditions. Let's put that in here so won't even have to wrestle with that. So both are under neutral conditions. So what that means for the, need to blow that up. So hold up. What that means is that when I add a hydride to that, so it's basically going to be here, right? Plus H minus. Put the electron. When I do that, that hydride is going to attack right here. Boom, right there. Is that right? Because that's the least substituted side. Yes or no?
Mm-hmm.
And then I'm going to pop that open. And then the second step is water. I'm actually going to go ahead and show that. Let me make sure I get to. Okay. This is going to be CH3. And this is O minus. Everybody see that?
Mm-hmm.
So when I pop the ring open, the carbon that's here is the carbon that's picking up that hydride. So that's a CH2. When the hydride adds, it becomes a CH3. All right, let me just draw it out so you can see it in case you're looking at this later. So the hydride hydrogen is there. Like so. All right. And then to quench that, that's what the water is for. So you basically just add a proton. All right, so you just add H plus, and that's going to give you this. Let me see if I can cut it. So I don't have to redraw it. rearrange some of this stuff so I don't, it's not all jammed up in one place. Come on. All right, hold up. I'm struggling with this lasso. Let me do a right step. All right. Now, let me see if I can, I'll just redraw it. All of that just to end up redrawing it anyway. Right, but you see you get the idea that once you pop the epoxide open, it's going to give you alcohol, or once you quench it, right? So this oxygen was negative, and then when I added the water, that was my proton source, so I could quench that oxygen and turn it into an alcohol. All right, what about on the other side? What's going to happen there? Let me see if I can. Let me cut this again. What's going to happen on this side? If I'm using a OCH3 as my nucleophile.
Wouldn't the OCH3 attack the least subsidized side?
Yes, it would. It's the same. When I'm doing epoxide opening, that's what happens. Whatever my nucleophile is going to attack the epoxide, because both carbons in the epoxide are partially positive, right, on both sides. All right. So the nucleophilic attack is going to happen. It can happen on either side, but based on the conditions, that's going to determine which side gets attacked. So here we know it's going to attack here and then pop that open. All right, so we're going to get the same type of product. The only difference is going to be that instead of a hydride adding to that carbon, is going to be an OCH3. So I'm just going to write the whole product out. All right, so notice this is that CH2 now, where the epoxide would the other carbon in the epoxide. So I have to show that bond to the OCH3. I can't just stick the OCH3 on there because that wouldn't be correct. It doesn't matter if it's facing how I have it facing, or if you want to draw it facing back this way. Either one is fine. That's symmetrical. All right. And then of course you know that this came. You'll have to do a quench step somewhere in there to protonate that and make it an alcohol. All right, questions about this? I apologize for the lasso incident.
And the quench step is basically when you said about the hydrogen.
Yeah,
bonded
so
to-
you can add in some type of acid or something like that at the very end to if you know you have a anion and you want to protonate it, you just add in like some type of acid. All right. So let's go to how much time I have? 15 minutes or 14 minutes. Let's go to here.
Dr. Russell, can you scroll back up, please?
Yep.
Yeah, to that part. Thank you.
Just let me know when you're done.
I'm done. I just took a picture.
Okay. Uh-oh. Why y'all didn't tell me this parentheses got jammed up in the S? All my little words got jammed up in the lasso incident. All right. All right. Let's go to this problem right here. I'm gonna make this a on your own problem. I think you can do it. I have confidence that you can do it. All right, let's go to here. All right, it's telling you here the type of reaction we're dealing with. So what is the Vidic and what does it do? What do we use it for? Synthesis of blank from blank. What do we use the Vidic to do?
Is it out? The synthesis of an alkene.
Said alkenes
Mm-hmm.
from what? You're right.
A ketone.
Ketones or aldehydes, right?
Yeah, or aldehyde.
Even though we know it's specific to ketones and aldehydes. Right, remember we talked about that, and I said you could do esters also, but it has to be it's a different type of reaction to convert esters into alkenes. All right. So what's the product? Let's do that first, and then we'll talk about the mechanism. So look at the starting materials. You got a ketone, right? You have a alkyl halide, triphenylphosphine, and a strong base. What's the product? And what's the shortcut we talked about?
Minus the. Yeah.
Is that right? This is what we're left with. Is that right?
Mm-hmm.
And this carbon right here is going to replace which atom in the carbonyl?
That oxygen.
Oxygen. Good. So the product is going to look like this. Right, with that carbon again from the alkyl halide. Replace the oxygen. All right, so I should have made that red. Sorry about that. Let me do that right quick. Right, that's the product. It's a you started with a ketone, ended up with an alkene. All right. The question is, how does it happen? That's what all this blank space down here is for. So we can figure out how it happened. What is this called right here? Anybody? I'll buy lunch for whoever tells me what that's called. You can put your Cash App in the chat box. Going once.
A reagent.
Close, but no cigar. It is one more. I'm gonna give one more shot at it.
Oh, Y line
Yeah, it's an
or E
Ilit.
line.
Is that right? Has a plus charge and a minus charge adjacent on two atoms that are adjacent to one another. All right. And where did the Ilit come from? And it came from the reaction of your alkyl halide with the base and triphenylphosphine. Right, that's where it comes from.
Okay, but then how does it get CH2 again if you took away the HBr?
No. Don't mix those two processes up. The top part is a shortcut. When I say subtract out HBr, that's a shortcut
Okay.
without going through the mechanism. The CH2 part comes in. Let me just go ahead and show you. So let me do that first, because this reaction happens in two phases. So the first part is Ilit formation. So you take your alkyl halide. I'm gonna write out the you react this with triphenylphosphine. Right? Remember that? So this is gonna come in, boom, in an SN2 fashion and react with your alkyl halide. All right, so once you do that, you're gonna have this. And that's positive. And then the base, which in this case was KOH, the OH minus is going to come in and pull off this proton. So that's how you get the Ilit. right? So the illet you make first. Remember I mentioned that when we talked about this reaction, how you stir together the alkyl halide, phosphine. While you're at lunch, when you come back, your illet is ready. Then you take a syringe and syringe in your aldehyde. Is that? I mean, it's literally the easiest reaction I ever did as a grad student.
Okay, but
All right, go ahead.
on the right side, it only has one hydrogen. Do you see what I'm saying? It says CH3 and then CH2.
Oh, you talking about? God dang it! You were right. That's a typo right here.
Uh-huh.
Yep, that's a typo. It should be CH.
Oh, okay.
Let me rewrite it. Thank you for catching that.
No problem.
Yeah, good eye. If you ever played softball,
Uh-uh.
that's what they call it when you get a bad pitch and you lick it off. Good eye. So what I'm gonna do for this, I'm gonna white it out. So when I post the notes, it'll be accurate. Actually, you know what? No, never mind. I'll fix it. I'll fix that. So we gotta stop here. I'm gonna fix that and post it to Blackboard when I post the notes. But I appreciate you pointing that out.
Wait, so
Go ahead.
that extra hydrogen came off when preparing the how do you say it?
Illit.
Illit.
Mm-hmm.
Oh,
So
okay, so
one of
that's
the hydrogens from the CH2 is gonna get removed when you make the illit, right? So you add phosphine and then use the base to deprotonate that carbon.
okay.
So that's how you end up down here with the illit. That's shown down here. And then that's what's gonna attack your carbonyl. All right, we can't finish the mechanism right now because it's 10:29, but we definitely will hit it Friday and finish this handout. But we'll do everything except for the aromatic stuff.
Okay.
All right. Any questions about anything? All right. I'll leave this up for a second for those of you who are still writing notes down. All right. So what we're gonna do on Friday is something kind of weird, but I think I'm gonna use the breakout rooms and just have 6-11 groups in the breakout rooms, have you work through 1 or 2 examples, come back together, and each group is going to be able to present their work. And then if you're in a group and you present your work and it's the right answer, then everybody in that group is going to get some type of reward. Not monetary, but points wise. All right. Any other questions about anything before we sign out?
Yeah.
All right. I'll see y'all on Friday. Be ready to work in the breakout sessions. I'm gonna keep them short because I know it's gonna be kind of weird. But yeah, be ready to
Will
work.
we learn our groups in class, or is that something you'll post prior to, like what groups we'll be in?
Say that again.
Will we learn what groups we'll be in for that?
Yeah. No, it's gonna be spontaneous with the groups.
Oh, okay.
I'm just gonna break y'all up based on who's logged in.
Okay.
Yeah, I don't want to do it ahead of time because right now we got 17 people and we got 35 people in this class. So doing it ahead of time is pointless, especially on a Friday. So I'm just gonna work with who's here.
Okay.
Yep. All right. Any other questions? All right, so I'm gonna stop recording, and I'm